at this point, everybody should know how to get information such as total mass of a compound from the number of moles of the compound or the molar mass of the compound. So if I write down here something like calcium carbonate, which we used last time, and if I give you 2 moles of that, you should be able to turn this into grams. That's already something that you should know how to do. For that, you need the molar mass of that, and then do the conversion. You also should be able to go from moles to moles using conversion factors. So I have a chemical reaction here. Let me put it on the board. And this may seem a little confusing at first. And of course, if you have other ways of visualizing how to convert moles to moles, by all means do it that way that you feel more comfortable. But I need to show you how you use conversion factors to go from moles to moles. Because these numbers, these coefficients, are precisely that, conversion factors. So for instance, if you have a question, how many moles of SO3 are produced from, and let me make it very easy right now, then we'll change it, 1 mole of O2, and you look at the stoichiometry, at the ratios, well, you see that 1 mole makes 2 moles. So the answer is right there in front of you, right? The answer would be 2 moles. But what if instead of that, I put 3.4 mole? Well, once again, in this example, it may look actually easy, but remember that these are conversion factors. So you can say, okay, according to the stoichiometry of the reaction, 1 mole of O2 equals 2 moles of SO3. That's coming from that balanced stoichiometric equation. And from there, you can get 2 conversion factors and choose the one that you need to do that. So, as we have done before, we have 3.4 mole of O2, and we want to convert that to mole of SO3. So we need to multiply by a conversion factor coming from that equality that will cancel out mole of O2 and leave me with mole of SO3. So I choose the one that has this on top. And put this one on the bottom. So yes, indeed, as you may have predicted, it was just a matter of multiplying the number that you were given by 2. But sometimes it's not that easy or that clear or that straightforward. And it's good to visualize it with conversion factors. So that is something that you should be able to do. Now, when we move forward in this chapter, some of the problems are going to involve multiple steps. And whenever you have a multiple step problem, you have to have multiple step thinking. You need to be thinking in logical progression to get to the answer. So let me see if I can show you what I mean by that. Can I erase this stuff? Yes. Okay. Action. And let's balance it. It's always good to practice. So we have iron reacting with oxygen to produce iron 3 oxide. Is it balanced? Well, we have 1 iron, 2 iron, so it's not balanced. We need to balance it. And this may not work with just putting a 2 here, but we can start there. So 2 there, 2 and 2, that's balanced. 2 oxygens, there are 3 oxygens there, so that's not balanced. Now, what if I double, and this is trial and error, what if I double these and go back? Well, now I have, why did I double it? Because 2 multiplied by 3 is going to give me an even number. And that's one thing that I need to be thinking about. That's what you thought, right? So 2 times 2 now is 4, right? So that's easy here because iron is by itself. We have 4 irons, 4 irons. What about the oxygen? 2 times 3 is 6. Well, that one is also kind of easy. Put a 3 there. And that's the balanced equation. So in this case, we don't have ones like the one I just erased. We have 4, 3, and 2. So it's important that you know how to get these conversion factors. If I were to tell you, okay, so you have 15.5 mole of iron. Instead of 4, you have 15.5. And the question is, how many moles of Fe2O3 do you get from that amount of Fe? Well, again, for every 4, you produce 2. So is there anything that we can do easily? Well, maybe in your head you can. But I'm not that smart, so I need to set it up visually. And I'm going to say, okay, I need a conversion factor that relates iron to iron 3 oxide. So I say 4 Fe equals, and let me be very specific, 4 mole of Fe equals 2 mole of Fe2O3. That's my equality. I want this into that. So I'm going to put it down. 15.5 mole of iron needs to be multiplied by a conversion factor coming from that equality. The one that leaves that on at the end, the one that cancels that out, so that would mean put that on top. And the other one on the bottom. Carry out the math, and you get the answer. So maybe in your head you thought, well, it's 4 to 2, so I'm going to just divide by 2, multiply by 2. Whatever you thought, to me, this is infallible. This doesn't fail. If I set it up this way, I can visualize what I'm trying to get, and I'm not going to make a mistake by trying to do it mentally. Now, what if instead of going from moles to moles, moles of reactant to mole of product, we had to go from grams to grams? Well, here, you cannot use these equalities because grams and grams are not the same for different compounds. The mole works, but the gram doesn't. So let me show you what I mean by that. In fact, I'm going to do it in front so that you see the difference. And we're going to use a different, well, we can use the same one. So what if I were to tell you, if you have 25 grams, 25.0 grams of iron, how much Fe2O3 is produced? In grams. I could be actually asking in moles, but that wouldn't accomplish much. So we have the stoichiometry. But we cannot just say, oh, well, if 4 equals 2, then 25 equals 12.5. That doesn't work. You have to use molar masses. So what we know is that this guy, using the molar mass of iron, can be converted to moles of iron. So on step 1, I'm going to convert mass of iron to mole of iron. That's my very first step, so that I can use the stoichiometry. Okay, so how do I do that? I take 25.0 grams of iron, and I multiply that or divide that by the molar mass of iron. So I look at the periodic table. What is it, 55.847? Let's just go with 55.8 for this problem. So now the problem is that 55.8 grams of iron are equal to 1 mole of iron. In other words, if I just take the molar mass and I put it here, I'm going to be multiplying grams by grams. So I need to, once again, visualize it as an equality. But this is the molar mass coming from the periodic table. Now I know that I need to put this on top and that on bottom. So it's 1 mole of iron is equivalent to 55.8 grams of iron. And if I carry out that operation, I get the answer. I did bring my calculator this time. I hate to be searching through the internet. So if you have yours, please verify my calculation. 25. 0.44, I agree, 4 or 5. 0.45. Let's look at the units. Grams cancels, grams cancel. 0.44, or 45 I said. 45. And what are the units? Mole of iron. I'm done with step 1. Okay, so we did step 1. I'm going to erase the molar mass of iron and describe to you step 2. So now that I have moles of iron and I have the stoichiometry of the reaction here, I can convert moles of iron to moles of iron 3 oxide, right? I can convert this to that in moles because I have this stoichiometry. So that's what I'm going to write here that I want to do. Convert mole of iron to mole of Fe2O3, iron 3 oxide. And for that we need the stoichiometry again. We have 0.45 mole of E2, of iron. I know from over here before that my conversion factor is this one right here. So I did that before, but again, it comes from the equality that I have right here. So I'm going to just put it here, 2 mole Fe2O3 is equivalent to 4 mole of iron. Not rusted yet. Once again, this helps me visualize everything to make sure that I don't make mistakes. So 0.45 times 2 is 0.9 divided by 4. So enter 2 times 4 divided Do you agree with 0.22? 0.224, yes. Okay. So 0.22 mole of Fe2O3. So now, we haven't answered the question. If we have 25 grams of iron, how many grams of iron oxide are going to be produced? Now, one assumption that I haven't mentioned to you is that there's plenty of oxygen. That's not limiting, because we're going to talk about limiting reagent very soon. But that has to be a given. So number 3, step 3, what do you think is going to be? But what would we label the step? Convert what to what?
Moles to grams?
Yes, convert the moles of iron 3 oxide to grams of iron 3 oxide. So convert mole of Fe2O3 to grams of Fe2O3. You see, we couldn't convert that directly from iron to iron 3 oxide. We had to go through moles. Grams to moles, moles to grams. All right, so how do we do that? We have the answer here, 0.22 mole Fe2O3. We need to convert it, multiply by a conversion factor that is going to come from the molar mass. We don't have it yet. So we need the molar mass of this guy. So that's an extra step, an extra complexity that is part of the thinking process that you had to be thinking about. So we need this molar mass. And once again, we learned that in chapter 8. How do we get the molar mass of Fe2O3? Well, we say 2Fe times, what was it, 55.85. I have it there. Let me use 58.8. And then we have 3 oxygens. Each one of them is 16. 159.6. Okay, 159.6. Let me just leave it there. Grams per mole Fe2O3. So now we have what can go there. This is again, this result, whatever it is, plus that result gives you that total. I'm taking shortcuts because you should know how to do that already. Okay, so if that's a molar mass, that means 1 mole of Fe2O3 weighs 159.6 grams. Wait a minute. I did it wrong, didn't I?
What do you mean you did it wrong?
Well, I put the molar mass here in the wrong place.
Oh, yeah. It needs to be on the...
I cannot cancel moles with moles. So, good for conversion factors, right? It helped me realize that I made a mistake. And this wasn't planned. It's a real mistake that I just made. So I needed to multiply by the molar mass, not divide by the molar mass like we did before. And that kind of makes sense, because we're going now back to grams from moles. So 159.6 grams is 1 mole. And that worked really well, because if I had not set it up as a conversion factor, if I had just said, oh, I'm going to multiply that by 1 and then divide by 159, I would have made a mistake. So now I can see that that cancels out, and whatever that answer is, in fact, the answer to the question that we had at the beginning. So 0.22. I get 35, but that's okay. So 35.1, if you are around 35, then I'm sure you did it right. What are the units? Grams of Fe2O3. So guess what? from 25 grams of iron, we get 35.1 grams of iron 3 oxide. That's just one problem. Now, the good news is that the very last topic that we're going to deal with, if you digest this one bite at a time, don't swallow it all whole, you're going to be fine. You need to take a step back, look at what is in the question, and then try to answer the question. Now, that's a little more spice to this whole thing. Because what do we know now? Well, we know that having a balanced stoichiometric equation, we can actually predict the number of moles of product if we start with certain moles of reactant. What we're going to do next is talk about what happens when you may have a lot of this but not enough of that, or a lot of that but not enough of that. This idea is called the limiting reagent. Can I erase this? Okay. And I really like an example from your book. It's kind of like my pancake example, but it uses a bicycle as the analogy for explaining limiting reagent. I'm going to put it on the board because I think it's useful. So to make a bike, you need one frame. Now visualize a bike. The frame is the main part of the bike, if you will. You need 2 wheels. We need 1 seat. And this is not a Tesla, but just a regular bike. And 2 pedals. Very generic bike. Equals 1 bicycle. Kind of bad writing there. So, let's take this scenario. What happens if you have uh, 5 frames, 16 wheels, 10 seats, and 20 pedals? Which of the components is limiting? And by that, I mean, it's limiting you the number of bikes that you can make. So this component is equivalent to which reagent? These are the reagents right here. And this is the product, just like in chemistry. And you can ask yourselves so many questions. Well, okay, with 5 frames, how many bikes can I make? 5 bikes, right? 1-to-1 ratio. With 16 wheels, how many bikes can I make? Don't look at the frames, just at the wheels. How many bikes can you make with 8 bikes? With 10 seats, 10 bikes. It's 1-to-1 ratio. With 20 pedals, 10 bikes, because it's a 2-to-1 or 1-to-2. So which of these components is limiting the number of bikes that you can make? Okay, so 5 bikes. The wheels is 8 bikes, so that's not limiting you. You can make more bikes than you have frames. So that's not the answer. 10 seats, how many bikes? 10 bikes, right? So that's not limiting. 20 pedals, how many bikes? 10 bikes, so that's not limiting. So it's only the frames, which is what you suggested before. So the limiting component, in this case the limiting reagent, would be the frames. That's exactly where we're heading, but we're going to do it with chemicals. And we're going to do it first with moles and then with grams. And that's where it becomes more calculation, because you need to be very organized at calculating what is needed. Okay. So that's the idea of limiting reagent. After that, we just have one more concept called percent yield, and that's it. We're done with the semester. So let's do a couple of problems with limiting reagent. So we're going to start with this equation. Nitrogen, and notice that I'm not putting the states of matter, the phases. That's okay. I'm just trying to, just trying to save a little bit of time. That's a 3. So in this stoichiometrically balanced equation, we know that 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of, this is called ammonia. Now, how much ammonia is produced if you have 10 moles of nitrogen and 3 moles of hydrogen? So this is a limiting reagent question. You know that for 1 mole of nitrogen, you need 3 moles of hydrogen. For 10 moles of nitrogen, you would need 30 moles of hydrogen, right? We can do that in our heads. So which one is limiting here? There's not enough of what? Of hydrogen. There's not enough hydrogen. So all we can say is that if I have this reaction, what I'm going to produce is 2 NH3 and have 9 moles of nitrogen left over, because I only consume 1 as per the stoichiometry, and 9 NO2 left over. Now with moles it seems fairly straightforward, but we're going to be playing with grams. Now, before we start doing more problems, I want to explain something about yield. And we're gonna explore 2 types of yielding. The so-called theoretical yield, and we're going to compare that to the real yield, which is going to be called just percent yield. How much we actually got. And let's take a look at that equation to begin with. If we were to convert this to grams, and let's do that, what is 1 mole of N2 in grams? Well, we need to look for nitrogen and multiply it by 2, right? So 14, roughly speaking, times 2, 28 grams of nitrogen. What are 3 moles of hydrogen in grams? So how do we do that? The molar mass of hydrogen is 1, but we have 2 of them. So 2 times 3, 6 grams. So the theoretical yield in this case would be that number plus that number. Because everything is being consumed, nothing is left over, we cannot create nor destroy matter, the theoretical yield would be 28 plus 6, 34. Now, let's see if that matches. So the molar mass of this is 14. There's only 1. That is 1 times 3 is 3. That is 17 times 2, 34. So if everything works okay and we have no leftover and the conditions are right, we are going to make 34 grams of ammonia from 28 grams of nitrogen and 6 grams of hydrogen. But what if you do the experiment and you end up not with 34 grams of the product, but with 30 grams? So the actual yield, let's say that we get only 30 grams. For whatever reason, maybe we lost some of this hydrogen to the atmosphere when we were mixing the two. Maybe some of the nitrogen also escaped. The point is that we did not get 34 grams. We need to be mindful of the fact that we cannot create nor destroy matter. We just had losses that went somewhere. So how do you manage that? Well, the percent yield of a reaction is calculated by taking the actual amount that you get, in this case 30 grams of product, you divide it by the theoretical one, the one that you were expecting to get, 34 grams, and then you multiply by 100. And that's it. Yes. So to get the percent yield of any reaction, you need to divide the actual yield, the one that you are given as the experimental product, divided by the one that you have to figure out as the theoretical yield. And you do that from the molar masses. And then multiply by 100%. So this is experimental theoretical from molar mass. And for that, and to explore that in more detail, we're going to look at a problem from, this one comes from the actual homework. I looked ahead and I got this from the homework. And this would be one interesting to ask ChatGPT, because when I was looking at the problem and I Google the name of the product of this equation, I got a different one than the book uses. So if you use the book to answer a question in the homework from the book, you're going to get the right answer. But if you use the internet to answer a question from the book, you may not get the right answer. So I'll explain what I mean by that in a minute. So any questions about yield? I mean, I think the idea of limiting reagent is fairly straightforward. The yield idea is a little bit more convoluted, if you will. But the two combined gives you a really good picture of what happens in real chemistry. So here we go with the reaction. Apparently you can make a pesticide called Sevin, S-E-V-I-N, by combining something called naphthol, C10 H8O. So this is called naphthol. It probably stinks to high heaven just by the name. How do I know? Anything that ends on OL in organic chemistry is an alcohol. And you know that alcohols kind of smell. I mean, rubbing alcohol smells. Ethylic alcohol or ethyl alcohol smells. So this probably smells. It's probably related also to the mothballs, naphthalene, which is another nasty chemical. Okay, if we combine that with something called phosgene, COCl, COCl2, and the name is that. We produce that pesticide with the formula C11H7O2Cl, and then a byproduct of the reaction is hydrochloric acid, HCl. And I believe the very first question in that problem went like this. Let me put the name. Of that pesticide. How much 7 is produced from, and the book, I'm going to give you the amount that the book uses scientific notation for this. 1.9 times 10 to the second kilograms. It's almost like the book reminds us not to forget that we learned scientific notation a long time ago. I hope you can make the conversion in your heads to decimal notation, and that is essentially 190 kilograms, right? The same thing. So how much 7 is produced from 1.9 times 10 to the 10 kilograms of naphthol? Now, assume unlimited phosgene. So we're going to assume that we don't have a limitation on the amount of phosgene. Assumption. Phosgene is unlimited. We're not even going to think of an amount. We're just going to ignore it. We're going to go with the stoichiometry of this. Now, the stoichiometry, and we haven't checked to see if it's balanced, but I believe it's balanced. So 10 plus 1, 11, 11, 8, 7, oh, wait a minute. Yeah, 8, 7 plus 1, 8. I got lost there for a second. 1 plus 2, 2. And then 2 chlorines, 1 and 2 chlorines. So it is balanced. So 1 mole of naphthol gives you 1 mole of 7. But we don't have 1 mole. We have 1.9 times 10 to the kilograms of naphthol. So what are the steps that we need to do to answer the question? Since we already did this once, I want to give you, 10 seconds to propose the very first step. What do you think we should do first? Say that again? Mass to moles. So convert the mass of naphthol to moles of naphthol. Yes. So let's put that. Grams. And of course, we need the molar mass of that compound. I'm not going to ask you to calculate it. I have it here. I think I did it roughly. 144 grams per mole. So that's 120 plus 16, 136. Yeah, 144. So we have 1 mole. Sorry. We have 190 kilograms. Now here's the problem. And you can do this in your head or you can do it on the board. Molar masses are in grams per mole, not in kilograms per mole. So you have to be careful. We really need to convert these to grams before we use the molar mass. Understood? I hope you see why. So 190 kilograms equals 190,000 grams. We don't need to go through the steps on how to do that. You should be able to remember that kilo means 1,000, so I just put 1,000, 3 zeros there. Now I can go 190,000 grams of naphthol. Multiplied by a conversion factor from the molar mass. So the molar mass is 144 grams per mole. I know I'm taking shortcuts, but I'm taking shortcuts that I think you already know that are needed to solve the problem. I mean, the information that you can get to solve the problem. That's what I meant to say. So, 1 mole of naphthol is equal to 144 grams of naphthol. And that's going to give me the moles of naphthol that we have in 190 kilograms. I did the calculation and I came up with 1,320. Can you confirm that? So this is equal to 1,320 mole. So we've done step 1 as per your suggestion. What do you suggest is our next step? So convert moles of naphthol to moles of 7. Yes. And for that, we start with 1,320 mole of naphthol. And this one should not be that complicated because 1 mole yields 1 mole, right? So guess what? If we set it up with a conversion factor, we're going to say 1 mole of 7 is 1 mole of naphthol. That's coming from this stoichiometry, 1 to 1. Was that step necessary? Probably not, but you know, it sort of clarifies how these things work. So the original question is, how much 7 is produced? I didn't even ask you in what units. So you could say, well, I'm done. I produce 1,320 mole. Well, let me rephrase the question. How much 7 in kilograms is produced? So we're going to have to go to kilograms. What do we need? What's the next step? I'm going to start with the word convert since I know that that's what you're going to say.
Convert moles back to grams.
Exactly. And we have to go to grams because the molar mass is in grams. I mean, we can add number 4, convert grams to kilograms, but we're going to do that on our heads. So 2 grams. Use molar mass as, I already calculated that for you, and that came from 12 times 11 plus 7 plus 16 times 2 plus 35 something. I came up with 206.45 grams per mole. So that's the number we're going to use. So set it up. 1,320 mole, 7. Multiplied by a conversion factor coming from the molar mass. So just straight 206.45 grams of 7 are 1 mole. If you carry out this operation, and I did ahead of time, I got I already have it in kilograms. 206 grams, I believe. Let's just do the math. Can you do the math and tell me what you get? 1,003. Enter 206. I cannot even read my own notes. Oh, 272,000. Yeah, that makes sense. 272,000. I'm going to leave it just with 3 significant digits. Well, 4 significant digits. Grams. And in my head, and I hope you can do that in your heads, this turns out to be 272.5 kilograms. I just divided that by 1,000. So we produce from 190 kilograms, 272 kilograms. Is that what I have here? Yeah, I have 270. I only have like 3 minutes left and I didn't go to the percent yield. But let me just tell you where we were heading with that. So I was going to tell you, okay, you have 700 grams of naphthol and 700 grams of phosgene. I want you to tell me how much 7 is produced and then what is the percent yield. So we'll do that on Tuesday next week, and then we'll start with the homework. In other words, we have the last part of the last problem that we were going to cover. And for the lab, we're going to do the stoichiometry lab, which I haven't touched. So I have no idea if I'm going to struggle with you a lot, or if you're going to do it faster than me because I'm going to struggle and you won't. Or I don't know. We'll take a look. I'm a little afraid of that exercise because I have never looked at it before.